Hello everyone, welcome to lecture 7. Here we shall be discussing one more criteria for detection. Okay, one more criteria for drawing a decision boundary. In the first lecture we saw that we had only class conditional PDF. If we had only class conditional PDF, how can we make a decision boundary that is optimum? That was the NP detector. We had that by the Neiman-Pearson criteria. After that, we saw that we had a little more information. I mean, way more information because we were given costs and the prior probabilities, respective prior probabilities of the events. And throughout, we are discussing only the binary scenario where there are only two possible cases. Either a signal is transmitted or it is not. Okay, so the hypothesis comes as only null hypothesis and the alternate hypothesis that we propose. And until I go into other spaces, we will be considering binary hypothesis for the time being until and unless specified. So right now, if there is a situation in which you don't know the prior probabilities and you are given only the cost and the class conditional PDF, so is there any way by which you can form a decision boundary or you can find a criteria for detection? That is precisely what is the min-max criteria for detection. So basically, if you just look into this, we are just discussing the different ways that would often come naturally to you if you sit with the problem. Under various circumstances, when we are having the luxury to have more information about a particular situation, or we have a little less information, or we have very less information, accordingly we are making the best detector. Okay, because now we are studying the detection theory, it's all about detection. Okay, so given the costs and the class conditional PDF, is it possible that we can have a decision criteria? The answer is yes. How? This is what we shall be looking into in this lecture. Okay, all right. So once again, our main idea would be to minimize the base risk. Here the R is subscript. Okay, our idea would be to minimize the base risk once again, but now we shall not be considering the prior probabilities. Okay, there would be a certain set of assumptions that would make the mathematics a little simpler. We shall be going on to discussing that. Okay, so basically you should be understanding this in this scenario. Only class conditional PDF we have NP criteria. Then we have only cost. We have min max. And if we have cost and prior probabilities with us, of course we would be applying the base risk to have the LRT there. Okay. All right. So let us start with a very basic formula that we had. So we know that under a given hypothesis, so we are talking about binary hypothesis. There is the null hypothesis and there is the alternate hypothesis. So we know that probability of detection is under the region Z1, and we have the alternate hypothesis into account. Okay, this is what we have studied. And if you are seeing this lecture for the first time, you can just go back and look at the previous lectures where I have in detail discussed everything how it comes. Okay, now it will be redundant to discuss that once again. So if we have the detection here like this, we also have the probability of being missed as Z0. So when it is in the region where it is not detected, that is Z0, but we have already sent, that means it would be under hypothesis H1. Okay, when is it detected? When the signal is sent, which comes under hypothesis H1, and we detect, that is the region is under Z1, so that becomes PD. And similarly, P miss is when the signal was sent, that means the PDF that we have to check here is with respect to the hypothesis H1, but because it was missed, that means it was not detected, it comes under region Z0. Okay, very beautifully we have this equation here following this. P of miss is equal to 1 minus PD. I think this is very trivial, right? So as you can see, these are just two different regions, and we have seen that these two regions don't overlap, and these two regions that are formed by the decision boundary like takes on the entire plane that we are dealing with. So basically PM plus PD is equal to 1. Okay, so this is another relation that we have. And if we talk about the probability of false alarm, that is the signal was not sent but it was detected, it was detected, that means it comes under the area Z1, regions Z1, and because it was not sent, the hypothesis is under H0. Okay, having said that, let us write the base risk. Okay, as we know, base risk is C00 probability of detected given H0 is transmitted, P0 plus C01 probability of detected H0 given transmitted H1 P1. These are the priors, okay, plus C10 probability of detected H1 given transmitted H0 P0 plus cost 11 probability of detected H1 given transmitted H1 P1. Okay, so this is the base risk that we have. All right, now we shall be rewriting it. We shall be rewriting the integration. So in the last lecture where we have decided the criteria, where the base decision criteria, where we had all the class conditional probabilities and the costs, everything, and the priors also. In that we had written this integral directly. Now let us replace, because we are not explicitly dealing with the integral, it's not necessary. So let us write it by that expression C00 P0, and let us write this entire expression by 1 minus PF. Okay, because this is what it is, right? Just a minute. Yeah, 1 minus PF. If transmitted is H0 and detected is also H0, then it comes to be 1 minus P of false alarm. The entire region comes to be 1 minus P of false alarm, because P of false alarm is under the region Z1 under the hypothesis H0. Okay. Likewise, we have C01 P1 and transmitted H1 but detected H0. We did not detect the signal, but it was transmitted. So it is a clear case of miss. So this is P of miss plus this C10 P1. Sorry, C10 is with P0, right? Yeah, C10 is with P0, and probability of detected H1 and transmitted H0. So this is particularly a case of false alarm. So I have P of F, okay, plus the last case, that is C11 P1 and transmitted H1 and detected is also H1, the hypothesis. So that means that we have, this has probability of detection because it was sent and it was detected as well. Okay, all right. So we can also write this PD as 1 minus PM. Okay, this is just a mathematical upbringing, nothing else. We are trying to simplify this term. Okay, so one thing is we will be putting in here to kind of reform it in the way that we would want it to have, is PM PD is equal to 1 minus PM. Okay, this is something that we'll be throwing here. Okay, another thing is we want to bring this entire expression in terms of P1, because here in this case we would be assuming that priors won't be available to us. Okay, so can we say that P0 is equal to 1 minus P1? If we write this, so you could have written it in terms of anything. You could have written it in terms of P1 or P0. It does not matter. I'm just choosing P1, just a 50-50 chance. Okay, there is nothing very special in assuming this. I'm just reducing the expression to how I want it to be. Okay, so if I put this 2 into this expression, I would be having R specifically in terms of P1, because this would be only the variable that would be left. Please understand that PD, PM, PF, C, these are all constant terms. Okay, the only thing that can vary is the P1, and that is the function of which I'm making this expression as. Okay, so this would come to be, see, wherever there is P0, you replace it by 1 minus P1. Okay, all right, P0 plus C01 P1 PM. So you arrange it like this. Okay, I have already arranged it. If you arrange it and if you take P1 into one place, this entire equation would become something like this. Okay, so as you see, we have the cost, the base cost as a function of P1 here. This is a very interesting thing to note. So we have this entire expression which is a constant, and this is an entire expression which is a constant. We can look at it as the parameters of this equation. So it is something like this, that R of P1 is equal to C plus M P1. Okay. So although we are seeing that these are constants, these are not exactly constants. So as to say, I'm just saying that our base risk will be varying according to this parameter P1. Okay. And according to this variation, we would need to decide how the graph would be, graph of RP1 versus P1 would be. Okay, this is one important notation to consider. So you can do the mathematics here, how the base cost comes, and you can also see that it would be arranged like this. Okay, all right. This is a function of P1. You could have made it as a function of P0. I leave it to your exercise in that part. Okay, so if I have a particular value of P1, listen to this properly. If I have a particular value of P1, if the value of P1 is fixed, then this C and M1 would also be fixed. Okay. And because this C and M1 would be fixed, we would have a particular point to consider. Okay. So accordingly, we would be having a particular graph of R versus P1. This is what we need to see at this moment. Okay. So there is one thing that we would be seeing shortly, that is this curve, this RP1, it is always concave down. In fact, it can be proven that it is always concave down. Under no circumstances can it be in any other form. It will always be concave down, no matter what. This can actually be mathematically proven, but I'm not going into that because we would be digressing from what we intend to do here. But it's not hard. You can take it as an exercise. Okay, just I'll also be giving a hint on how to do that, but later on. Let's take this. Okay, so for example, as I said, for a particular value of P1, you will have a fixed notation of C and M1. Okay, so in that way, for example, if P1 is 0, P1 is 0 means no transmission is happening. Okay, there is no transmission, absolutely no transmission. So if there is no transmission happening, what will be the probability of detection? Will you detect anything if there is nothing transmitted? No, right? So the probability of detection would be 0. All right. If there is nothing transmitted, of course, the probability of miss will be 1. Okay. If there is nothing transmitted, then the probability of false alarm will also be 0 in this assumption. Okay. So we'll always be missing it, right? If there are no signals transmitted. So this is an ideal scenario that I assume for this specific purpose. And for example, if I take P1 to be 1, that means the signal is always transmitted. Okay. This prior information I have, this is always transmitted. If that is the case, then probability of detection ideally would be 1 because we would always be detecting it. Miss would be 0, hence, because the probability of detection and miss are very intimately related. And probability of false alarm will also be 1 because it's always transmitted. Okay, this is the ideal scenario that I'm having. This is the ideal scenario I'm holding. You can reflect on it, why this is the case. As I say, with certain assumptions, with certain simplistic assumptions, things become very easy for us. Okay. Also, this is an assumption for us. Let us assume that C11 is greater than C00. Okay, for the sake of simplicity, you can have that in any order, does not matter. But in this case, in this specific case where we are assuming this in a specific way, C11 would be greater than C00. This would help us in certain assertions that we'll be seeing. So for example, if P1 is 0, If P1 is 0, you have PF as 0, and also you have just PF as 0. So if P1 is 0, this entire term cancels up. This entire term gets cancelled. PF from here gets cancelled. So here you are left with only C00 like this. Okay. And if you move forward, if you have 1 here, if P1 is equal to 1, you see PD is equal to 1, PM is equal to 0, PF is equal to 1. So if PF is equal to 1, this entire term will be cancelling. You would be staying with C10 here. So if, for example, P1 is equal to 1, let us expand the term, okay, to see what is the case. So from here I'll be having C10. Okay, for let me take a little dark. Okay, from this term we'll be having C10 plus. If P1 is equal to 1, PM is equal to 0, this term does not stay. PM is equal to 0 plus C11, I have this term, minus, if PF is equal to 1, then C00 gets cancelled, and here minus C10 PF is equal to 1, so I have minus C10. So C10 gets cancelled. For P is equal to 1, I have C11. These are the two extreme points. Okay, and the curve we would be having would be somewhat like this. It would always be a concave down curve in all the cases. Okay, to just show that it would always be concave down, you can make a proof by the method of contradiction. You can prove that it always is concave down by taking a kink, by assuming that a kink is possible. Please take it as an exercise to be performed at your home if you can. Okay, if you're not able to intuitively visualize why it is so, then please comment. Maybe I shall make a video if the demand is more. Okay, all right. So this is what we are standing with right now. Okay, all right. So here there was an assumption in this particular case that C11 is greater than C00. Okay, but to have a good base curve, for correct detection when there is no false alarm, if we assign equal cost, it would be a very effective system. Okay, if we are giving more bias to C11, it would be nonetheless not a completely worn out detector, not so, but we won't be having a very good base curve here, because we are weighing C11, the cost of the signal being transmitted and being detected, much more than the cost of signal not being transmitted and not being detected. Okay, so this does not make sense, right? So for example, in the next scenario, we are trying to like little bit kind of we are trying to manage it a little bit. We are trying to make it a little more realistic. Okay, this was an extreme case, like whatever you assume not C1 to be, it will always be concave down like this. Now we have this particular scenario. Let us assume the cost of making right decisions to be 0. Okay, this is the ideal scenario. This is when we can have a very good base curve. The system incurs cost only when there are wrong decisions being made. Okay, if there are right decisions, the system does not incur any cost. This is the optimal condition of making a detector. Okay, so in this particular case, if both C00 and C11 is equal to 0, then the curve which was like this initially would become like this. It has been proven that, it has been shown rather, that it is always a concave down curve. So it will be somewhat like this. Okay, this is the optimal detector. Okay, and for the optimality, you can see that there is one point where this particular risk takes the optimum value, and this is exactly where the slope is 0. Okay, so when the slope is 0, then the risk has an optimum value. This is exactly the criterion for the min max decision boundary, or the decision criteria rather to say. So basically, like if you differentiate it and put it to 0 for optimum value, if you just differentiate this, so you will be getting m, and if you put it equal to 0, you will be getting the optimum value of p1 for the optimum value of r of p1. Okay, so we will be coming up with m is equal to 0. Now this m, what is this m? M is this entire expression. Okay, now if this particular expression C01 Pm plus C11 1 minus Pm minus C00 1 minus Pf minus C10 Pf, if this is equal to 0, then what you have is, see, I have already said C00 and C11 is 0. So C00 and C11 is 0. So we are left with C01 Pm is equal to C10 Pf. Okay, so this particular expression that we get is called the mean max criteria. Okay, because we develop the entire thing in terms of conditional probability and the cost. We have the conditional probability, we have the cost, we can bring up this criteria. Okay, so under the optimal assumption that we don't associate any cost for the correct decisions, we have from the logic that the curve of base risk in this particular scenario would always be concave down. We derive that the optimality condition by the min max criteria can be this. So if you have any problem where you are given the conditional probability and you are told to calculate a threshold via the min max criteria, then you can just close your eyes and put this expression. So costs will be given to you and the conditional probability under both hypotheses will be given to you, and you will be told that find the decision criteria. Even if it is not said that find it with min max criteria, you precisely know what you have as an information and what you should use. Okay, so finally, to conclude this lecture, I have the entire min max criteria to be summed up with this particular expression. C01 Pm is equal to C10 Pf. So the costs are given, and please note this, that this criteria is derived only under the condition that C00 is equal to C11 is equal to 0. Okay, if this holds, then this expression can have a meaning. If this does not, for example, C00 and C11 has different values, so you need to approach it by this entire expression. There are problems where it won't be 0. In that case, please take this expression and make it equal to 0. You will have the individual costs and you will be given the individual class conditional probabilities. If that is so, you need to use this entire expression. But to make things simple, the way we do in most of the problems that will be given, you would be made to assume, or you would be given straight away, that C00 is equal to C11 is equal to 0, because that makes the most sense. Okay, why would we assign cost to right decisions? We won't in an ideal scenario unless and until we have a very specific thing in mind to build our detector. Okay, so this lecture concludes the theoretical concept of min max criteria for detection. In the next lecture, we shall be taking on this concept further with a problem, and then we shall be getting into a very important concept, that is the receiver operating characteristics, the ROC curve. Okay, the ROC curve is a very important concept in the field of machine learning also. You assess a model's performance with its ROC curve, but ROC means receivers operating characteristic. Now, what does it mean, receiver operating characteristics? This comes from this specific lecture. The ROC, the concept of ROC curve by which we decide how a model performs, comes from this, comes from the estimation and detection theory. We shall be looking into it, how this is the case. By a better interpretation of how the ROC curve is, you can actually visualize the accuracy metrics and performance of your machine learning model if you are into that field in a much more better way. You would have a different sense of insight of how it is there, because most of the cases you are not told how an ROC curve is formed. You are told that it is just formed. Here we will be seeing the basics of how it really happens. Okay, so next lecture is going to be very important in this context. So I hope you enjoyed this lecture, this particular criteria. If you have any question, please feel free to comment. Let's meet in the next lecture. Thank you.